Hello, Math 30-2, and welcome to the season finale. Actually, this might be the series finale of Math 30-2 online for you guys. Actually, we'll say season finale because this might happen again for a future 30-2 class, but not you guys. We will be back in person learning on Monday. At least that's the rumor I keep hearing. So this is it. This is the last day of online. And I think we all agree that you're tired of listening to my voice through a computer screen. And I'm pretty tired of making these videos. So that's great news. I'll get to see all your beautiful faces again. You get to ask questions in a more normal way. And it'll be a wonderful, wonderful time. So let's get at it. We're going to keep today short and sweet. We're just going to finish off Unit 2 and then call it a day because it's Friday. Unless you're watching this on a different day. But it's supposed to be Friday when you're watching this. And you've had a long week with this online learning. If you're watching this video in the year like 2030, we're in the middle of a pandemic right now. It's pretty sweet. Okay, let's get into it. We're doing perms and comms. We're now going to do some at least and at most restrictions on perms and comms. And we're also going to mix in some probability to just see how miserable this can get. So, example 16. In a standard deck of 52 cards, how many different 5-card hands could you make? All right, the first thing you need to start asking yourself, because we're now at the end of this unit, the first thing you have to ask yourself is this a perm or a comm? And you're going to ask yourself that basically every time you get a question where it starts asking about different hands or different arrangements or different anything. That should be the first instinct. Perm or comm? The difference, a permutation is when order matters. A combination is when order doesn't matter. In this question, it says, in a standard deck of 52 cards, how many different 5-card hands could you make? So when you get dealt cards in a game, does the order in which you pick up your cards matter, or is the first thing you do when you pick them up, rearrange them anyway? And that's what you do, right? Like, it doesn't actually matter which order you get the cards. Once they're in your hand, they're in your hand. So for us, this is a combination question. Combinations use the formula NCR, where N is the number of cards you're choosing from, and R is the number of cards you choose. So for us, there's 52 cards. So I go 52. I put a C because the order does not matter in which I get those cards. And then I choose 5 cards, so it's 52 choose 5. To put that in your calculator, you type 52, then you hit math, you hit the right arrow all the way over to PRB, and you hit number 3, NCR, then you hit number 5. And you get that the number of ways you could get dealt a 5-card hand is 2,598,960. Cool. Now, let's make things a little more complicated. Part B. How many hands could you make with at least 1 diamond? So now there's a rule we have to follow here. We need at least 1 diamond. That's pretty complicated. So if you wanted to do that, you'd have to calculate how many hands have 1 diamond, how many hands have 2 diamonds, how many hands have 3 diamonds, how many hands have 4 diamonds, how many hands have 5 diamonds. That's a lot of work. So instead, what we're going to do is we're going to take all the possible hands you could be dealt, and we're going to subtract away how many ways can you get no diamonds. If I subtract away all the hands that have no diamonds in it, I'll be left with only the hand that has all diamonds in it. Or, sorry, not all diamonds, at least 1 diamond in it. That's called using the complement. If we take everything in the group and subtract away what you don't want, you'll be left with what you do want. For us, we already know that this is the answer for total possible hands. So that is our number for all. 2,598,960. Then we want to subtract away no diamonds. No diamonds is a little bit more complicated. To figure out no diamonds, you have to think about how many cards you can actually choose from. So in a deck of cards, just so you remember, it's been a while, there's 13 diamonds. If you don't want any diamonds from this deck of cards, that means you no longer have 52 cards to choose from. You have 52 minus 13 cards, meaning that you have 39 cards that you actually do want to choose from. So it's 39, choose 5. That represents 39 cards I want. They're the non-diamond cards, and I want to choose 5 of them. If you put that in your calculator, you get 2,598,960. Subtract 39, choose 5. 575,757. It's kind of a cool number. 575757. If you subtract those numbers from each other, 259,8960 minus 575757, you get your total number of hands with at least one diamond is 2,023,203. That is the number of cards with at least one diamond in it. Now, it's been a while since we've done these kind of like card questions, so that might have been a bit of overload. If we look at question C, this will give us a good little perspective on how to do these card questions. It says, how many hands could you make with at most 2 kings? At most means you don't want more than it. So this means you want a hand with no kings, or means, actually no, we're going to write the actual word or, and we're going to break this down. So you'd be happy with no kings, or you'd be happy with 1 king, or you'd be happy with 2 kings. But you don't want any more than 2 kings. So those are the 3 situations you'd be okay with. You'd be okay with getting dealt 5 cards and none of them are kings, 5 cards and one of them is a king, 5 cards, 2 of them are kings. Now we're going to break this down a little bit more. So when I say no kings, that's 0 kings, 5 different cards. So I'm just going to put D. Different than a king. The word or in math means that we're going to add things. Situation 2, I would be okay with getting 1 king, but then I only have 1 card in my hand, so that means I need 1 king and 4 different cards that aren't kings. Or means I'm going to add the situations. 2 kings. That means I would be happy with getting 2 kings and 3 different non-king cards. From there, we need to break this situation down even further. For 0 kings and 5 different cards, I need to somehow pick these cards. We don't have to worry about picking no kings. That's just going to happen on its own. To pick the 5 other cards, you have to ask yourself, how many cards do I want if I don't want any kings? Well, in a deck, there's 4 kings. That means there's 48 non-kings or different cards. So when I go to select my blue section here, the 5 different cards, there's 48 to choose from, and I want to choose 5 of them. That represents 48 non-kings, choose 5. Plus this green situation. We need to do this in chunks. So we're going to do the 1 king first. The first thing I do is pick a king. There's 4 kings to choose from. I need to choose one of them. That is now in my hand. And then I have to pick my other cards. There's 48 other cards to choose from that aren't kings, and I need to choose 4 of them. Combined, that gives me 5 cards chosen. 1 king and 4 other cards. In between these two combinations is a multiplication sign because it's the word and. You're picking 1 king and 4 different cards. And means multiply. Plus, this yellow one, I need to pick my 2 kings. Well, there's 4 kings in the deck. Choose 2 of them. And there's 48 non-kings in the deck. Choose 3 of them. Perfect. Now you need to go ahead and calculate these things so that we can add up all the answers. So when I look at this blue situation, I go 48, choose 5 in my calculator. It should be a lot of numbers, yeah. There's 1,712,304 ways that you can get those. Plus my green situation, if I put that in my calculator, I get, 778,320 plus, if I do my yellow situation, 4 choose 2 is 6, multiply that by 48 choose 3, and you get 103,776. You add those numbers together, and that will tell you the total number of ways that you could get at least 1 king in your hand. And the answer is 2,594,400. That's a lot of possible hands, but it makes sense that it's a lot of possible hands because it's more likely than not that you don't have a king than you do have a king, right? Like, think about playing cards. Like, there's a good chance you don't get any kings. All right. That is some hard perms and columns stuff right there. You might want to even just pause, rewind, and watch that again. Sometimes the second time is like, oh, now I see where he's getting those numbers. This would also be a good moment to pause and pop into the Google Classroom and be like, Mr. Kennedy, where did you get that number from? And then I can help you out. If you're feeling confident, we can move on to here, and we can look at a couple of old diploma questions. So this one is actually straight from a diploma exam. It says an octagon is drawn with a point on each of the vertices. If a triangle is to be made inside of the octagon by connecting 3 dots with lines, how many different triangles could be made? Okay, an octagon. Let's draw this. This question was on a diploma. It did come with a picture. So an octagon is like this. Oh boy, then my octagon's going to be whack if I don't get the lines straight. Computer. This might be the world's worst octagon, and I'm using straight lines from a ruler. Come on. This was the octagon drawn. Yikes. It's an 8-sided shape. And the vertices are the corners. Perfect. This was labeled. This was actually on a diploma. You got a picture. It looked a lot nicer than this, but it was there. The question now says, an octagon is drawn with a point on each of the vertices. If a triangle is to be made inside the octagon by connecting 3 dots with lines. Okay, so imagine you did that. Let's say, okay, I just connect three lines. 1, 2, 3. I've now made a triangle. They want to know how many different triangles could be made. Well, that's going to be a lot because I could go 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Right? And you're going to notice that you're going to be able to draw a ridiculous amount of triangles. So there's no way that drawing it is going to be the right answer. I've seen people try doing that. Don't do that. It's not going to go well. When you get to a question like this on a final exam, you have to think to yourself, there's got to be a logical way to solve this. It's not going to be by drawing it out. There's got to be a process. And then think to yourself, it's got to be perms and comms, because all the other units have more like numbers involved and aren't so wacky. So when you read a question like this, think logically and think perms and comms. So if we're thinking through that lens, when I build a triangle, 1, 2, 3. If I'm thinking perms and comms, I need to think, does order matter? And then does order of what matter? Well, what I just did was I drew lines in between dots. Does the order in which I pick those lines matter? If I did this one first, and if I went straight up first, is that different than if I built the triangle by doing that line last? So if I went and built it like this, is that a different triangle? And the answer is no. That's the exact same triangle. That means that the order in which I'm picking my corners doesn't matter. This is a combination question. Even though it didn't even seem like perms and comms, it in fact was perms and comms. Because what you're doing is you're taking 8 corners and choosing 3 of them to connect together. When you do that, it makes a triangle. The order doesn't matter in which you pick those 3 corners, as long as you just pick 3 corners. You put 8, choose 3 in your calculator, and you get 56 different triangles that can be built in that octagon. Good luck drawing all 56 of them and not losing track. With perms and comms, you are going to get questions you've never seen before. And I can't possibly give you every situation in the world because it's just unlimited number of questions that they could make. So with that being said, the best thing you can do is learn how to think logically through questions. The best way to get good at that is to practice like crazy. So in your key booklet, you should be doing these perms and comms practice tests, practice questions. There's explanations in there. You need to practice. It's what will make perfect for perms and comms. All right, number 18. A class of 8 girls and 12 boys has been selected to make a committee of 4. If the committee must have both a male and female president and both a male and female vice president, how many different committees could be made? Okay, I've got all these people. What I want to end up selecting is I want to make 1 male president and 1 female president and 1 male vice president and 1 female vice president. Perfect. That's an ugly way to start it off. Essentially, that's what they wrote out though, right? Yeah, 1 male president, 1 female president, male vice president, female vice president. So essentially what we're doing is we're choosing 2 males, 2 females, right? I mean, they make it sound more complicated than it really is, but when you write it out and look at it, it's like, okay, they just chose 2 men and they chose 2 women. The question is, how many different committees could be made? So how many ways could you choose those 2 men and those 2 women? The first thing you should always ask yourself is, does the order matter in which you pick them? And in this question, The order matters. The reason the order matters is because when you choose the men, for instance, the first man you choose is the president. The second man is the vice president. They now have roles involved. So maybe you want to be the president, but not the vice president. So you might want to be picked first, right? It makes a difference. So this is an order matters questions. That means it is a permutation. The first thing we're going to permutate is the men. There are 12 boys to pick from. We want 2 of them. And means multiply. We're then going to choose the 2 females. There's 8 females to choose from. The order matters. We want 2 of them. This says there's 12 boys, order matters, pick 2 of them. And there's 8 girls, order matters, pick 2 of them. You put that in your calculator. 12p2 equals 132. 8p2 equals, I think, 56. But let's make sure. 56. And we are multiplying those numbers together. You do that, you get 7,392 combinations or permutations for that committee. Hoorah. All right. The last thing we're going to do today is some probability. This is about as hard as perms and comms will get. So they're going to take perms and comms and they're going to take probability from unit 1 and they're going to mash them together. The best way to do these questions is to remember that probability equals what you want divided by what's possible. So in question 19, it says, what is the probability of drawing a queen or a king from a standard deck of 52 cards? Okay, break this situation into 2 parts. The first part is calculating what you want. What you want to draw is a queen or a king. That means there's 8 different cards that I want to draw. The order does not matter in which I draw that card, and I'm drawing one of them. You put 8C1 in your calculator, it equals 8 ways that you could draw a queen or a king. I knew there was 8 cards because there's 4 queens and there's 4 kings. 4 plus 4 equals 8. Then calculate what's possible. Well, what's possible is that there's 52 cards in the deck and you just choose one at random. That would equal 52. I then can answer the probability. The probability equals what you want, 8 divided by what's possible, 52. If you put that in your calculator, you will get a decimal. You get 0.15 if you round it. If you math frac it, though, you get a better fraction of 2 divided by 13. Both of those are good answers. 8 over 52 is also a good answer, but you should simplify it to 2 over 13. As soon as you see probability, go want, possible, calculate. For part B, what is the probability of drawing a heart, or a card that is a heart, replacing the card, and then drawing an ace? This is tricky. When you replace cards, replacing the card, that changes things. The reason why it changes things is perms and comms, if you're using them, assumes that you aren't replacing things. And it assumes that once you pick something, you can't pick it again. So to do this question, we're going to have to break it down a little bit. We're going to break it down into what we want and what's possible. Okay, what we want to draw a heart and then draw an ace. Perfect. First card has to be a heart. There's 13 hearts in the deck. The order does not matter, and I need one of them. Then I put the card back in the deck, and I draw again. So now I have to keep these combinations separated, right? The reason I'm keeping them separated and using a multiplication in between them is because I replaced the card. So it's like a whole new draw. Then I need to draw an ace. There's 4 aces in the deck. I need to choose one of them. If you put that in your calculator, you'll get 13 times 4. That means there's 52 things that you want to have happen. What's possible is not 52 choose 2. Sometimes people are like, well, there's 52 cards and you're choosing 2 of them. That's what's possible. That's not right. The reason that's not right is because that assumes you didn't replace the card. Because you replaced the card, you have to draw them separately. So you draw the first card. There's 52 of them. Choose one. Then you put the card back and you pick another card. There's then 52 in the deck again, and you're choosing one again. That turns out to be 52 times 52. 52 times 52 equals 2,704. We then can do our probability. Probability is what you want, 52, over what's possible, 2,704 things. You put that in your calculator. You get 0.02. If you math frac that, it's 1 over 52. Uh, 0.02 would also be acceptable. So what you want, what's possible, and then calculate. Okay. Last slide of probability. So this says, Mr. Kennedy is selecting a 4-digit PIN for his debit card. What is the probability he selects a PIN that doesn't have any repeated digits? Perfect. This is a great probability question. Soon as I see that word probability, I am breaking this into 2 situations. Situation 1 is what I want to have happen. Situation 2 is what possibly could happen. We'll start with want. What I want is to repeat digits. Doesn't have any repeated digits. Well, if I was to do this question, I'm actually going to use the fundamental counting principle, right? We learned that 2 days ago. So I would have 4 numbers in my PIN. In the first number, I could pick any of the 10 numbers there are. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. In the second digit for my PIN, I could pick any of the other 9 numbers because I don't want to repeat. In the third spot, I could pick any of the remaining 8 numbers because I don't want to repeat. And then I could pick any of the remaining 7 numbers. Again, because I don't want to repeat. You go 7 times 9 times 8 times 7, and that tells me that there's 5,040 ways that I could pick a password in which those numbers do not repeat. That is what I want to have happen. No repeated digits. What's possible, though, is that you have 4 spots. And in that first spot, you could pick any of the 10 numbers. In the second spot, you now don't care if you repeat numbers. So there's still 10 different choices. Right? I can pick any of the 10 for that spot. For the third one, I can still pick any of the 10 because I don't care if I repeat or not. And the last password, or the last number in the password, is 10 as well because I don't care if I repeat. You put that in your calculator and you get 10,000. Then you have to calculate your probability. Probability is what you want, 5,040 divided by what was possible, 10,000. You get 0.504. If you math frac that, you get 63 over 125. Those are your options. Cool. Number 21. Why don't you try it? Pause the video, test it on your own, take your time, unpause it, see if you got it right. All right, this video says, some friends are going to get pizza. They have 10 different toppings to choose from and must choose 4. That's important. They have to choose 4. They can't just choose 1. What is the probability? Boom, that word, probability, that immediately signals to me, break this situation into 2 things. Break it into what do you want to have happen, and break it into what's possible could happen. What is the probability their pizza will include bacon and pineapple? Okay, so what they want is they want to have bacon and they want to have pineapple. This means that there's actually only 8 other toppings they're going to choose from, and they need to choose 2 of them. The way that I like to represent this is that they need to pick their bacon first. Well, there's one way to pick bacon. You need to pick it. So one option for bacon, choose that bacon. And you need to pick pineapple. There's one option for pineapple. You must choose that one pineapple. And then you pick the other 2 toppings. There's 8 other toppings to choose from, and we need 4 total toppings, so that means we need to choose 2. Notice that I'm doing combinations because the order doesn't matter in which I pick these ingredients. All that matters is that I'm picking ingredients to put on top of the pizza. Just to break that down, because I feel like that maybe wasn't the most clear. 1C1, that is your bacon. 1C1, that is your pepper or your pineapple. 8 choose 2, that's your other ingredients. If you put that in your calculator, I believe you're going to get, is it 56? 28, not even close. Oh, I was thinking per. There's 28 pizzas that you want. You want bacon and pineapple. So there's 28 pizzas that have bacon and pineapple. What's possible, though, is if we don't care about what the ingredients are. You could have bacon, you could have pineapple, you could have neither, you could have one. It doesn't matter. You would say there's 10 toppings to choose from. The order doesn't matter. Pick 4 of them. You go 10, choose 4, equals 210. And now that I know what I want and what's possible, I can go 28 divided by 210, and that will give me the probability that I have a pizza with bacon and pineapple. 0.13 repeated. If you math frac that thing, you get 2 out of 15. Is the probability you get a pizza with bacon and pineapple. Cool. Last question. When selecting a 3-person committee from five boys and 5 girls, what is the probability of randomly selecting a committee with at most 1 boy? That is about as hard as it could get. You got probability, you got at most, you got a committee. That's a hard question. If you hit pause, give it a shot, see if you get it right. It's the last question we're going to do today, so take your time on it. All right. Let's tackle this. When selecting a 3-person committee from 5 boys and 5 girls, what is the probability? Soon as I see that, I break my question down. And I'm breaking it down into 2 situations. Situation 1 is what I want to have happen. Situation 2 is what possibly could happen. I then keep reading the question. What is the probability of randomly selecting a committee with at most 1 boy? Okay, now we have multiple situations. One situation I'd be happy with is no boys. And that means you have no boys, 3 girls. Or I'd be happy with a situation with 1 boy, 2 girls. but I do not want more than that. So those are the only two situations I want. I want no boys, 3 girls, or 1 boy, 2 girls. Now let's try to do the math for it. So if I want no boys, 3 girls, well, there's 5 boys. The order doesn't matter because they're not getting jobs. They're just being put on a committee. And I want to choose 0 of those boys. And so multiply. There's 5 girls. I want to choose 3 of them. This that I just wrote represents no boys and 3 girls chosen. Or, remember, or means that we're going to now add 1 boy and 2 girls. Well, there's 5 boys. I now want to choose 1 of them. And means multiply. There's 5 girls. I want to choose 2 of them. That represents 1 boy, 2 girls. If you put those in your calculator, you do 5, choose 3. You end up with 10 plus 50. 10 plus 50, that means there's 60 ways you could get a committee with at most 1 boy on it. Cool. What's possible? When we start to talk about what's possible, you ignore everything that specifies people. So for instance, I don't care if I'm picking from boys or from girls. When I'm doing what's possible, all I see is that there's 10 people. And I need to choose 3 of them. I don't break it down into boys and girls. I just mash them all together and I pick 3. If I go 10, choose 3 in my calculator, I get 120 things that are possible. This means that the probability of selecting at most 1 boy would be 60 divided by 120. That is 0.5, which is 1/2. That is the probability of selecting at most 1 boy. Cool. That's it. That's it for Unit 1 and Unit 2. When you come back to school on Monday, we are going to kick things off with Unit 3. We should finish the entire review by the end of the week. Maybe we'll go into Monday the week after that, and then we will have our little midterm where you can reassess your last 3 units, and then we'll do some practice diploma questions. All right. Take care of yourselves. Have a great weekend.